Okay, let's our discussion. Okay, so what we will do in hypothesis testing is we will have the inductive So what we're gonna do is, from sample, we will make conclusion about the population. What will we conclude? It's called parameter. That consists of mean, then variance and proportion. And the reason why we care about these three parameters already discussed in the previous meeting, previous class. So when we talk about the parameter mean in sample, we will use a symbol like this, and then for variance S, and for proportions is and for the populations, for means, X bar, S, small letter S, and then P, and for the population, we use mu, and then sigma, and P. And for this purpose, actually we will utilize what we call central unit here, CLP, is justify when we have enough number of samples, it will follow the normal distribution probability. Okay, the large samples refers is like more than 30 samples. Data will follow normal distribution property. And what is normal distribution probability? So the data will follow like bell shape. It form like bell, right? In childhood era, don't use like the electrical, the conventional cell. So it almost like the cell, the shape. It means like most of the data will how to say, we will be in the middle, so like we can if we divide it into two parts, it will like have the same proportion, the left and the right side. It means also that mean, median, and modulus will have nearly the same value. Okay? So it represents the x is the value and the y represent the frequency, so number of the data. So for example, if this value is represent the weight, means this is also in centimeters. So this here is the value of the mean of the weight or the median or the modulus. And left side from the mean means it's will be smaller, and the right side is the right side of the mean will have the larger number of weight. Okay. But actually it will not stop here, because if we use the normal distribution probability model right away, it will be very difficult, because like you will have different numbers of value depends on your samples. Or depends on the objects. So when we observe about the height, means it will have number of height. If we observe about the weight, it means it will represent the weight. And different populations mean will have different different value, right? So the later on the scientists, because actually this is have the same characters, so the scientists already simplified or make the generalized normal distribution that is called standardized normal distribution. Okay. So because all the data form in this kind of this kind of distribution probability actually can be standardized. So when we call standardized normal distribution, convert to mu equal to 0, and then the variance equal to 1. That's why when we call normal distribution, we will have like mu and variance. Variance shows the what we call it. What's the English of sebaran? Should we distribute the range of its data, right? So when we say that the range is 1, means here if it is the 160 centimeters, means the range for the next data will be if the range is equal to 1, mean here is 159, then 158, and so on. Or if we say the range is 2, means 152, 56, 54, and so on. And also the larger part means 162, 164. This is to represent the range. Actually not the range. Yeah. Later can you help him? If I remember what the word for the sebaran, that's the variance. So in the normal distribution, means the mu will represent the real number, and the also the standard the variance will standard deviation will represent the real number of variance of standard deviations. But in normal distribution, the mu will convert into 0, and the variance or standard deviation will convert into 1. Okay, so when we have data like here is 160, and then in other country maybe 168, but all these kind of normal distribution can be standardized into standardized normal distribution. And when we already convert to standardized normal distribution, we can easily compute analyze the data, and then make computations and draw conclusion. Okay. So how do we make the convert? Actually, we have the So it will be based on the formula. So we see that the normal distribution and standardized normal distribution actually have the same CDF, and for the PDF it will be depends on the value of mu and variance, where the in standardized normal distribution the value of mu is equal to 0 and the variance equal to 1. So when we put 0 and 1 here, we can get this formulation for the PDF. What is PDF and what is CDF? Later it will be explained in detail in, I think, statistic. That's not statistic. When I check, actually it's not in statistical descriptive. I need to check again. So for statistic, do you remember what kind of courses that will you take or need to? Is there any kind of, because I don't remember the new curriculum, so it's significantly different from the one that before I went to school to study. So it's okay. So I will not explain it in detail, but what we will utilize in the hypothesis testing is the standardized normal distribution. Okay. Why it is very important? Because when we use the standardized normal distribution, actually it's already formed into a table. So when we talk about the standardized, still here we'll talk about the frequency. But this one will not mention about the real number, but it will show about the C value. So when we say about, for example, this is the mean. The C value for mu is 0, and when we for example observe the number of height 162, it will convert to another C value. For example, here means 0. Example 0.1 until like the extreme value is, for example, maybe 150. Here Z 3.5. 9.9. Okay. Also the same when we, for example, observe another type of data, still hate but another populations. For example, here 172, for example, mean the mu it will convert to z equal to 0, and for example here 173 equal to 175, it will equal to z 1.3, for example, and here maybe we have 270 the height, like z 3.9, and it's the same pattern for the other the opposite for of this graph. Okay. And for that, so we can generalize and then utilize the table that already formed by the scientists. Okay. So, until this point, any questions? Okay. And so from the standardized normal distribution, it's already have a table. So the upper row, it shows the number of z. So the first column and the first row, it will represent the value of z. How to read it is this first row is represent the first value and one number after the dot, and the upper one is the second number after the dot. So for example, when you call the C value 3.9, here means this is the C, right? It means this number is represent the C equal to mean 9.99. Means this number represent the C equals to minus 3.94. Okay. Also the same here, for example, the next slide. For example here, this one. So 2.9, if we have, for example, here 0.01, means 2.91. This we will take, or it represent the number. And for the middle, actually it represents the area. So this one when the is the y is the frequency and this is the value. For normal standard dash normal distribution, this is the value, and the area is the probability. So when we have all the area, means the probability equal to 1. And when we only care about the half of the area, this one means the probability is equal to 0.5. Okay? That's why you can check when the C is equal to 0, the probability should be 1.50 or 50%. Okay? So the number here represent the area under the line. Okay? Why do we care about the area? Because later on we will check the number based on this area. Okay. So when we care about the mean of the population, for example, we will check or the hypothesis testing. We will not conclude only one number, right, about the mean or variance or proportion, but it actually we will we hypothesize or we guess that the mean will the value of the mean is fall under this range. So whether it smaller than this number or larger than this number or between these two numbers. Okay. And then the area that we exclude, this one is called the error or alpha. Last time we discussed about the type. There are two types of error. Type 1 error and type 2 error. So in this kind of hypothesis, we will only utilize type 1 error, the alpha. So actually it means we realize that we will have error or we exclude, like for example, if we use 10% of alpha, we realize we probably wrong in or we make mistake in conclusion because 10% of the data we already exclude. So to minimize the error actually means we use the very small alpha. what it the alpha represent, because the smaller the alpha we use, means if we use to area, means the alpha we divided into 2. The smaller the alpha, the larger the range of area that we included, means the smaller the probability that the number of we wrong to take to draw the conclusion about the mean, because like the conclusions that we draw means that the mean is the range of the means is in this, like for example one for the height 145 to 195 for examples. Of course, the larger the range, means the smaller the probability that we exclude the actual mean of populations. Okay? Can I go to the... Yeah. Okay. So, okay, maybe like test first. Let's practice for how to interpret so when I say C equals to 1.56, define the 1.56 here. What is the probability value for the C 1.56? P here is probability. From the table, .65, sorry, 1.6 here, and for the 5 here, means what is the number in the middle for 1.65?
0.950.
0.955, then
0.
0.529. Okay, it represents, means the area. So when we read the standardized normal distribution is from left side to the right side, because another distributions, the way it reads will be like from right side to the left side. Okay, means the area under the Z equal to 1.65, it's 0.95, 05 and so on. So the other one that is excluded is only 0.05. Okay. another type of distributions model, distribution probability model that we will use for hypothesis testing is students T distribution. Actually, it's like have the same characterized with the C or normal distributions, because the shape also the same. It have bell shape, but the difference is it will be depend on degree of freedom. So we have P, degree of freedom. The background or the history of T distribution, because actually not all data we can draw from the large number of samples. Sometimes even to get 30 samples is very difficult for us, right? For example, for your class, even the total of populations of IUP students, not more than 30, right? So how can we take sample for, until 30? So the scientists actually who draw this kind of distribution is a students. So they have the project and then make experiment, and after that they have this conclusion and draw some and make one new kind of distribution probability model. That's why it calls students T distribution, because those group of students name this project as T project. So they find that they already found that actually the number of even if the number of samples less than 30, it can also form the kind of this model. Actually, this form is generated by this formulation, the PDF. So using this PDF or probability density functions, it will have the same, or we can use it to draw conclusions about the hypothesis. But they add one more variables, that is degree of freedom. Degree of freedom is formed from the number of sample minus 1. So when you have like 10 samples, mean the degree of freedom is only 9. Okay. How to read the table? Actually the same. So the except for this the degree of freedom. So the table is the same, like when you have the alpha, but here the upside is the alpha, and the row, first row is the alpha. You remember, it's alpha is over here, the excluded, So, and this is the degree of freedom. So we can check. The alpha is, for example, here 0.5. So we see with the degree of freedom, for example, we say 30. See, 30. Degree of freedom is number of sample minus 1. Means if degree of freedom is 30, equal to number of observation or sample 31. Okay. So if we use degree of freedom 30, means our observations or the sample we have is 31. We can see that when the alpha here is 0.05 and the degree of freedom is 30, means the t, because this is to the t, is equal to 160, 1697. It's almost the same with the C value. That's the T. Okay, and then how we apply to the hypothesis testing. So when we before we discuss about the calculation, so at first the step of hypothesis testing, first we need to determine the objective of the hypothesis testing. So whether we want to hypothesis test, or we have first about for example, the weight, or it is the weight, or about the for example, the age, right? Or age or life expectancy. So it depends on the case. Define the case and the objective, and then formulate. Like before, we already discussed, when we use or we formulate about the hypothesis, first we need to define the null hypothesis and the alternative hypothesis. Okay, then based on the case and the formulation, actually we need to define what kind of statistic test that we will use or utilize. So for the we already learned two type of distribution model that can be used for statistic test in hypothesis. That is standardized normal distribution, or t-test distribution. Or later on for variance we will use chi-square. But we will discuss about what is chi-square when we talk about variance hypothesis test. And
I have a question. From the previous assignment that you gave, is it a question about hypothesis testing?
yes, yeah,
The 8 point of the question?
yes.
All of them?
Because I mean like actually the calculation is very simple, right? You just need to calculate the z, and then when you get z, you compare it with the z alpha, and then draw conclusion whether it is rejected or fail to reject. Only those two.
For this type of hypothesis testing, the last step is to draw the conclusion.
Yes.
What do we draw? Is it like this or
No, just make the conclusions. Draw conclusion means like make conclusions. So with our conclusions, actually only two, right? If reject null hypothesis or fail to reject null hypothesis.
So we have a question. So as I say in the assignment, as the example, so if it's less than 0.05, so that means it's reject. I want to ask you like about this 0.05. Is it as a constant? Like we use it usual, or it can change?
Can change. Actually, 0.05 represent this area. 0.05 is the alpha, right? So when we use the 0.05 as alpha, mean we know that the we will let 0.05% of theta to be fake or not included in our conclusions. For example, I forget about the case. What is the questions? The questions, what is it about?
Hot and versus cold.
Hot and versus cold. And the other.
Breathing frequency, then hot and cold breathing frequency.
Eight questions, right?
Yeah, 8 question. automobile company. Average mileage.
0 point is 0 point lifespan, right? Okay, so for lifespan, so this is the lifespan. In standardized, the Z is equal to 0, but here they want to know if the lifespan, for example, the mice with an average lifespan 32 months will live to be about 40 months old when 50% of the calories diet decrease. Is there any reason to believe that new 0-4 street if 60 mice that are placed on this diet have an average lifespan of 30 months with a standard deviation of 60.5 months. So from the sample, they took samples 64 mice, right? These 64 mice the standard deviation, the lifespan average or mean, it's found to be have the 36 month lifespan. the standard deviations. Standard deviation is S, is it covariance mean as square. But they already mentioned standard deviation only 5.6. Okay. So what we need to do is convert this number into Z. So we can compare with the normal standard deviations. And then we can calculate Z into the X bar mean mu can use this Newman. First, what we do, so the objective is want to know about the lifespan of the mice. So first we formulate the hypothesis, means the null hypothesis is the mu equal to 40, and we want to declare the alternate is less than 40. And we know that this experiment is taken from sample 64, and then the mean that get from this sample is 38, and the standard deviations of the population is 5.8 months. So then the statistical test, because like we have larger than 30, means we can use the Z or distribution. Or also called standardized normal distribution. Okay, then we calculate the Z X bar mean, mu norm, mean. So 38 64 minus 2. What is square root of 64? 8. And then means 5.8 divided into 8.
0.725. 725.
Okay, then the result
Minus 2.75.
minus
2.75.
point
7. No, 2.75.
oh 2.75.
Yes.
Means here is the C equal to 0 if minus 2.75 here, right? Usually there are two kind of drawing conclusions. Yeah.
This is for the example on the PowerPoint. Example for
No. The example for the
for 10.
10.19. Okay. So the next, what we do, there are two kind of ways to draw conclusions. Here the question is compare the p-value, or first we use p-value. Actually p-value represent the area under the line, because it's p here means probability. Okay, so we need to check this minus 2.75 in the table. Minus 275 is here, right? Means 0.002980. Okay, means it's from here. Only 0.002. Or this is 0.2%. Okay. So the p-value is 0.02. So when we use alpha, example 0.5, the p-value, if the p-value is 0.002, means p-value less than alpha, right? Because this is solutions, when the p-value less than alpha, we fail to reject null hypothesis. Okay. Reject hypothesis, null hypothesis means we agree that the mu null is less than 40. Okay. Because actually, why we use this kind of hypothesis frames, because actually we never know what the exact number of mean, right, of the population. So what we can do is we guess that this, when we say the mu or the mean or the average of population is this number, it actually will be in this range, right? Because we can, as long as it is in this range, we agree that the mean actually in this number, because we don't include some numbers, right? But if it is fail to be in this range, means we also fail to reject the means we need to reject the null hypothesis. Okay. So when we use p-value, actually we compare the area with the alpha. But another way is we convert the number of this alpha into z value. Like when we use alpha equal to 0.05, like before, we know that the z value is minus 1.65, right? Like before. So for example, we check here when the alpha is 0.05. This one actually between minus 1.64 and minus 1.1. Something. So actually here is the exact 0.05, means like 40 something. So some use this, so 1.645 or 1.65 is also okay. Then we compare if the C that we calculate less than C alpha, means we reject null hypothesis. But if it is more than C alpha, we fail to reject null hypothesis. So there are two ways. Just directly use the alpha, the p-value, compared to the alpha, or then convert the alpha into z value and then compare the c of the alpha with the c of the you calculate from the observation.
So can you repeat the ways?
There are two ways. First, use p-value. When you use p-value, you need to search the p or the probability of the c that you calculate. For example, in this part, you find that the c is minus 2.75. Then you search in the table how is the p value of this minus 2.75. In the table you find that minus 2.75 the p value is 0.00298. And then you compare this p value with the alpha. If the p value less than alpha, reject null hypothesis. The opposite means if the p value larger than alpha, fail to reject null hypothesis. That's the first way.
How can we get the alpha?
Alpha is defined usually because this is this is the type 1 error that we realize or we define. We will use like 5% or then 10% or 1% or 0.1%. Okay. The second way, we still use the z that we calculate, but what we convert is the alpha. We convert the alpha into z. So when we use alpha 0.05, means we look in the table what is the z value for 0.05. Okay.
So the question in for example in midterm exam will be like this.
Yeah.
All the question.
Yeah.
So more
the
into like
base-
story based.
Yeah. Okay. And don't forget, you need to not only not until calculate the test statistic and drawing conclusions, but you need sometimes the students forget to explain what is the reject null hypothesis. So what you need is like to not only back to the question. So for the example in this case, the question is not only reject the null hypothesis, but reject null hypothesis means that the lifespan of the mice actually less than 40 months. So for the sake of point or grade, we still give the point for this step, but like for the perfect point means need to finish and need to answer the questions. So I think the same case with the t distributions. So the Later on, we will like the next meeting. There are some types of sample means. For one sample, there are some there are two conditions for hypothesis testing of mean. First, only one sample. The other is two samples. One sample for this kind of questions or case, we just care about one observation. But for two samples, mean we have two populations that we need to compare. But the other one is the conditions for the variance. So some case the variance is known, but the other case the variance is unknown. Actually, in the real case, it's very difficult to have populations that we know the variance. Actually, if we know the variance, automatically we can compute the mean, right? But how can we like compute the mean if we? It's ridiculous when we ask about the mean while we already know the variance. But to simplify, usually we just use the historical data about the variance, and then we try to draw conclusions about the mean. That's why we have two kind of conditions: known variance and unknown variance. Okay. I think I already put also in the slide about the difference of formulation that we will use when the variance is known and the variance is unknown. Okay. Okay. Any other questions?